It's small. Yeah. I'm like, oh, it's I told my mom one and then she said she awesome. We'll see. Maybe she's giving it a little there. Did they? I don't know. It was one to us. It's for mine. We had them before. They got a bunch.
But we worked last.
Oh, really?
Honestly.
I saw it there. This one? It was next year. It was last. It was like red. Yeah, it was a normal color, but it was small. But then as a kid, it's too small to put anything really big, which is good. So just stop buying stuff. You use it for lunch. You just like use it for. Take it out.
Yes, it's
Like, sorry, yeah.
complicated.
But at least I can put a jacket there. I don't think it's big enough. It's like it's big. You don't believe it's unfold. I feel like this is why you're not believing from them. You can put like your phone in there and your some stuff. Yeah.
But I misinterpreted the rules. But that we could.
Yeah, it is bigger than it was.
No, that's what we do. No, I never.
I like when they shoes stuff. Like candles, it's so and stuff. They do a lot of candles like during the fall.
All right, it's 4 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing? How's everyone's spring break? Good, good to be back, hopefully. Well, it's the end of semester, so we're gonna be quite busy from here up until May. Speaking of which, one of the first major things that we need to do is we have midterm 2 coming up. Now I did decide to postpone it. So originally it was scheduled for next Thursday, April 17th. We are a little bit behind from where I want to be, so I want to just make sure we have enough time to cover everything with Fourier transforms, which is the last topic for this for this big unit before the midterm. So I did decide to postpone it until the following Tuesday, April 22nd. So that's 2 weeks from today. Okay. There is one more homework that I want to give you guys before the second midterm. So I'll give that to you guys probably on Thursday. Just because homework 5 is still out there right now. And what we're going to cover today is going to help you with the last problem on homework 5, which is the half range expansions. Okay, so that's kind of the most important things that I want to talk about. So for probably the first half hour today, we'll talk about half range expansions, and then we'll move on to start talking about Fourier transforms and the Fourier integral. Okay. All right. Any questions I can answer before we get started for today? Okay. Yeah.
When you uploaded the new homework, it didn't look any different from the other.
So they it was kind of a major, very minor kind of correction for part 3 of homework 2. Part 3 of problem 2 had kind of an extra term in that expansion right there. So but I'll double check. I might have accidentally uploaded the same file twice, but I'll check to make sure that's the yeah. Okay. All right. So let's go ahead and get started. Okay, so before we left for spring break, we were talking about Fourier series expansion. So let's take a minute just to kind of review that, just because it's been a couple weeks since we met. Okay. So a Fourier series expansion is basically you can think of it as kind of an alternate representation of a periodic function. Okay. And the idea with the Fourier series expansion is that we can represent any periodic function as a summation of sine and cosine terms. Okay, so the idea is like this. And so for any given function f of t, right? So this f of t here is some periodic function. So this is equal to a0 plus summation n is equal to 1 to infinity of an multiplied by cosine of n pi t over L plus bn sine of n pi t divided by L. Yeah. Okay. So you can think of the Fourier series expansion as kind of like a transformation. And so instead of a generic function, periodic function, we can represent that as summations of sine and cosines. And so it kind of changes our how we kind of represent that function. Okay. Okay. And this has a lot of benefits. And so, kind of pulling from the homework 5, you'll see that, a lot of the functions that are given you in that homework are discontinuous functions, okay? So this periodic function that we're representing, this can actually be a discontinuous function. Okay. Discontinuous or disjointed or piecewise function. Okay. But by doing this Fourier series expansion, by doing this representation with sines and cosines, we then represent it as a continuous function. Right? So everything on the right here, cosine is very much a continuous function. It doesn't have any kind of weird breaks or any kind of discontinuities. Same thing with sine. Sine is a continuous function. And so by doing this, right, everything on this side of the equal sign is a continuous function. So we're going to get more into it a bit, once we get into the Fourier integral and the Fourier transform. But one very important application for Fourier is to kind of smooth out these functions. So a lot of times you're going to have situations where you have a signal or some kind of function that has these very sharp discontinuities or it's very disjointed. So you can use a Fourier series expansion or a Fourier integral to smooth it out to, make it a little bit more easy to kind of represent and work with. Okay. Now, the main thing that you have to do, or the main kind of piece of calculation here, is to compute the values of these coefficients, right? So we have a0, an, and bn, okay? So when a problem asks you to find the Fourier series expansion or compute the Fourier series expansion, what you're actually going to be computing are the values of these coefficients, okay? So an, bn, a0, these are the coefficients of the expansion. And we have expressions for these as well, okay? So for a0 is simply just the mean value of the function. So it's 1 over 2L, or excuse me, 1 over L, or 1 over 2L, that's fine. Integral from minus L to L of f of t dt, okay? So that's simply just the average value of the function across one period of the function, okay? An is equal to 1 over L, integral from minus L to L of f of t cosine of n pi t over L dt, okay? And then Bn is equal to 1 over L integral from minus L to L of f of t sine of n pi t over L dt. Okay. So these three equations right here, these are the equations we can use to compute the Fourier series expansion coefficients, okay? And what you're going to get from these expressions after you compute them, they are going to have different values depending on the value of n, okay? Where n here, all of these n's, right? Well, it only shows up in two places. These n's correspond to the summation in the Fourier series expansion, right? And so we're going to have different coefficients depending on the value of n. Okay, so if you look back at the examples that we did before spring break, if you look at problem 2 of the homework, that's kind of what this is all about. So computing these coefficients, putting them in the expansion, and then you get your Fourier series representation. Okay, so that was mostly just kind of a review of everything up until this point. Any questions on this so far? Okay. All right, so one of the other kind of really important simplifications that we talked about before spring break, was simplifications for even and odd functions, right? Because if you look at these three formulas here, these are basically three integral expressions that you have to evaluate. And even though, maybe these aren't, the worst integrals that you have to do, it can still be kind of tedious to do all three of these integrals for every single problem, okay? So oftentimes what we like to do is we like to simplify our process if we know something about the pattern of our original function. Right? So basically, we can assume that some of these coefficients are 0, depending if our underlying function, if our original function is even or odd. Right? It is probably the best thing that you can do to kind of simplify your work. And I would definitely get practice in recognizing even and odd functions because it will help you on the exam. This exam, it's a little bit longer than the first exam. I'll kind of tell you right now. And so if you can kind of correctly identify if the function is even or odd, that's going to save you a ton of work to do on the exam. Okay. Okay. So for an even function, remember, the criteria for an even function is that it is symmetric across the vertical axis or across the y-axis of our plot. Okay. So one example, I think that we did last time, right, is if our function looks like this. Right, so this is just one example of an even function where, if you consider kind of the vertical axis here as like a mirror, okay, we can see that we have the same function mirrored on both sides of this line here, okay? Mathematically, the way that we represent even functions is we say that if we plug in kind of the reciprocal or negative value of our function, so f of minus t, that's going to give us the exact same value as f of t. Okay. So that is our kind of our criteria for an even function. F of t is equal to f of minus t, or f of minus t is equal to f of t. Okay. Okay, so for even functions, we can basically assume that our Bn terms are going to be equal to 0. Okay. Right. So we're not going to have any contribution from the sine terms of our Fourier series expansion. And that makes sense because sine, right? Sine is an odd function, whereas cosine is an even function. So if our underlying function is even, then it's probably going to be best represented using even functions of cosine. Right? Okay. So it makes sense that all of the non-cosine terms, all of the sine terms are equal to 0. So that means all the bn's are equal to 0. Okay. Okay. Now let's look at odd functions. Okay. So odd functions, the way that you look at the symmetry for odd functions is a little bit trickier because you have to look at symmetry across kind of a diagonal line. Okay. And so the diagonal line is either given by f of t is equal to minus t, or f of t is equal to t. Okay. Okay, so if we draw that out, so f of t is equal to minus t looks something like this. Okay, so this dotted line is f of t is equal to minus t. Okay. So an odd function is going to be symmetric across this diagonal line. So if you plot out the function, so let's say our function is this kind of Harry Potter lightning bolt thing. Okay. So our function kind of goes down like this, and then goes up like this, and then down like this. Okay. And so if you look at the dotted line that we drew, you can see that our function is symmetric about that line. So this function here is considered an odd function. Okay. Now the mathematical definition of an odd function is that if we evaluate our function f of t at a minus value, okay, and so let's say we evaluate it at f of minus t, that's going to give us minus f of t. So basically, the minus sign kind of pops out in front of our expression. Okay. So in the case of an odd function, then we can make the simplification that all of our even terms are going to be 0. So that's an, of course. So an is equal to 0. And also, a0 is going to be equal to 0 as well. So for an odd functions, it actually saves you 2 integrals to do. So you can assume that an and a0 are equal to 0. Okay. And the reasoning for this is the same as our even functions. Is that when you have when our underlying function is odd, it's best represented by other odd functions, which is sine. And so it makes sense that all the cosine terms, all the constant terms are equal to 0, and all that we're left with are just the sine terms, or all the bn terms. Okay, so this concept of kind of even and odd functions, very important for Fourier series representations. It ends up saving you a lot of work for these, for these slides. Okay. All right. Any questions on this? Okay. All right. So that brings us to kind of the main topic for today, which are called half-range expansions. Okay. And a half-range expansion actually builds off this idea of even and odd functions in a way that kind of applies it in kind of a clever way. Okay. So what is a half-range expansion? So, if you've noticed, from all the problems that we've done so far and all the problems on, problem 2 on the homework, you know, I've defined the function for you for a full period of the periodic function. Okay. Okay. So basically our functions have been defined from negative L to positive L, right? So we go into the negative axis and the positive axis, okay? But what if our function definition is only defined for half of this time? Okay, so let's draw it out. So let's draw our coordinate axes here. Okay. So normally, you know, if you look at the two functions that I had above when illustrating even and odd functions, you know, we define our function to the left of the vertical axis and to the right of the vertical axis. Okay. But what if we only defined a function to the right of this, you know, of this axis here? So what if we only define our function for t is greater than or equal to 0? Okay. So we don't know what the function looks like for t is less than 0. Okay. Okay, so what can we do in this case? Because, you know, if you look at all of our expressions or all of our formulas for our coefficients, you know, they require us to integrate from on the negative side. Okay. And so how are we able to compute our coefficients if we can't perform our full integration? Okay. Well, in this case, you know, we can make some assumptions, right? So we can kind of fill in the blanks in terms of what we think the function is going to look like on the other side. Okay. Okay. Which kind of sounds ridiculous, right? So, you know, it kind of seems like we're just kind of making stuff up just to make our computation convenient. But there's kind of a clever way that we can do this that, you know, kind of maintains a lot of the information that we want from the Fourier series expansion. Okay. Now, there's two main ways that we kind of assume what the function looks like on the other side of the vertical axis, right? We can assume that this function is an even function, or we can assume that this function is an odd function. Okay. Now, both are going to have different Fourier series representations, and they're both going to look different as well. So let's see what it would look like if we did an even half range expansion. Okay. And so if we did an even half range expansion, so I'm going to do that in blue. Okay. Then we know our even function here is going to be symmetric across the vertical axis. And so, you know, it would look kind of something like this. So in blue right here, this is our even half range expansion. Okay. So basically assume that we have even symmetry and we can reflect our function across that vertical axis. Okay. The other option that we have is if we do an odd half range expansion. So our symmetry there is going to flip. And so instead of being symmetric across the vertical axis, we're instead symmetric across a diagonal line. And so in red right here, we have an odd half range expansion. All right, and then depending on whether we do an even half range expansion or an odd half range expansion, that's going to change the coefficients that we solve for as well, right? And so, you know, if we go back to kind of our even and odd assumptions, we know that for an even function, our bn's are going to be equal to 0. But our a0 and an are going to be non-zero. So those ones we have to actually compute, okay? Now, the way we compute the coefficients for half range expansion is a little bit different. Just because, you know, we're only given the function from 0 to L. And so our integrals here are going to account for that. And so our formula for A0 is going to be 1 over L integral from 0 to L of f of t dt, okay? So we're no longer integrating from minus L to L because our function technically isn't defined from minus L to 0. So we're only integrating from 0 to L. And then our ANs, we're going to do something similar. So we're again only going to integrate from 0 to L, and then we're going to assume the function is the same on the other side. So we're going to do an integral here, 2 over L, integral from 0 to L, f of t, cosine of n pi t over L dt, okay? So since we're only integrating on half of the domain, we double the amount here. So we put that 2 on top. Okay, so 2 over L instead of 1 over L. Okay. And then for our odd half range expansion, right? So for an odd function, we know A0 is equal to AN is equal to 0. Okay, so we're not going to compute A0 and AN for an odd function. We're only going to compute BN. And we're going to make the same modification here. So we're only going to be integrating from 0 to L, and we're going to you know, account for this by multiplying the entire thing by 2. Okay. So this is equal to 2 over L integral from 0 to L f of t sine of n pi t over L dt. Okay. So half range expansions, you know, is not anything terribly new compared to our, you know, our usual Fourier series expansion. It's just that you have to kind of make an assumption of whether your function is going to be even or odd. Okay. A lot of times when you're given a problem with the half range expansion, a lot of times they'll tell you to do both. So compute both the even and odd half range expansions. Or sometimes they'll just tell you to do one. So sometimes they'll just tell you to do the even half range expansion or the odd half range expansion. So it's something you just kind of have to kind of look at each problem, kind of see exactly what it's asking you to do and compute accordingly. Okay. Any questions on this before we jump into an example? Yeah.
So we wouldn't graph it ourselves and see, like.
Oh, you
we
can.
wouldn't be able to tell if it's odd or even.
You definitely can. You can definitely graph it if you want. But the most important thing are the coefficients. Yeah. Graphing will definitely help you visualize. So if you want to plot your graph afterwards and see how it matches up, that's definitely a good thing. Any other questions on this? Okay. All right. So let's do an example. Okay. So let's say that we have the function t squared. We have f of t is equal to t squared. Okay. But it's only defined from 0 to 1. Okay, so if you want, so the problem in the actual notes actually does both the even and odd half range expansions, but I do want to move on to Fourier transforms today. So let's just look at the even half range expansion. But the details for the odd half range expansion in the notes as well. But it's, you know, it's more or less just more integrating, you know, polynomial terms and sinusoid terms together in the same. Okay, so for our even half range expansion, we're going to use these two blue formulas that we have up here. So one for A0 and one for AN. Okay. Okay, so let's compute A0 first. So A0 is equal to 1 over L integral from 0 to L f of t dt. Okay. Now remember L here is our half period. So our half period here is just 1. Okay. Since this function here is only a half function, we know our full period is going to be 2 here. Because this function should go from -1 to 1, but we're only given the function from 0 to 1. And so because of that, our value for L is equal to 1. Okay. And so if we plug that in, we get 1 over 1 integral from 0 to 1. F of t here is t squared dt. Okay, so we have a simple integral here of just a quadratic function. So let's just go ahead and perform that integral. So we integrate this, we get 1 over 3 t cubed, evaluated from 0 to 1. Okay. We plug in our integration bounds here, we get 1/3 of 1 cubed minus 0 cubed, which is just 1/3. So that's our first coefficient. So A0 is equal to 1/3. So that's kind of the average value of the function within that interval. Okay, now let's compute AN. Okay, so our formula for AN is equal to 2 over L integral from 0 to L f of t cosine of n pi t divided by L dt. All right, so let's plug in our expression for f of t. Let's plug in our value for L. So this is equal to, L is still 1 in this case. And so we have 2 multiplied by integral from 0 to 1, t squared cosine of n pi t dt. Okay, so we have a polynomial term t squared multiplied by cosine to the sinusoid. So the best way to do this integral is to do it by parts, or you can integrate by table. Okay. Okay, so I'm gonna do a table just because, you know, we can kind of do everything kind of in one step there. Okay. So in one column of the table, we're going to do one part of this function, which is just the t squared. Okay. So that's going to go in the first column. And the first column, we're going to be taking derivatives. Okay. So I usually call that the u column. And then the other column is going to be the other part of our function, cosine of n pi t. That's going to go in our dv column. And remember, in that second column, we're going to be taking the antiderivatives of those expressions. Okay. Okay, so first thing, let's go down the left-hand side column and let's keep taking derivatives until we get 0, basically. Okay. So derivative t squared is just 2t. Okay. And then derivative 2t is just 2. Okay. We're just taking derivatives of everything in that column. And then one more, the derivative of 2, which is just a constant, is 0. Okay, so we have kind of 4 entries in this table. Okay, and then we integrate everything on the right-hand column. So there's going to be 1 over n pi sine of n pi t. Okay. We take the integral one more time, we get minus 1 over n pi squared cosine of n pi t. And then we just integrate one more time to get the 4th row. And that's going to be minus 1 over n pi cubed sine of n pi t. Okay, so whenever you need to do kind of integration by parts multiple times in a row, this is kind of the easiest and I think most convenient way to do it. Okay, so you separate into 2 parts. One part where you can take derivatives and eventually get it to 0. Other side, you just take integrals. And then what you do is you go diagonally downwards. So you have t squared multiplied by 1 over n pi sine of n pi. Okay. You have 2t multiplied by minus 1 over n pi squared cosine of n pi t. And you have 2 multiplied by the entry that's kind of to the right and down. So minus 1 over n pi cubed sine of n pi t. Okay. And remember, whenever you're integrating by table, you need to alternate the sign. So first one's going to be positive, second one's going to be negative, third one's going to be positive. Okay. Okay, and then now let's kind of write out this expression here. So if we write it all out, okay, first expression is a positive t squared over n pi sine of n pi t. Okay. So that's the result of our t squared multiplied by its diagonal kind of neighbor here. Okay. All right, second term we have minus, and then so that minus comes from the integration by table, and we have another minus sign that came out from the columns. We have minus minus 2t all over quantity n pi squared. Cosine of n pi t. Okay. So of course, those 2 negatives are going to cancel out and become positive. And then our final term here is a minus 2 all over n pi cubed sine of n pi t. Okay, so a little tedious. It's always a little bit tedious to do these integrations, but I think this is kind of the easiest way to do this. Any questions on this so far? Have we got this integration here? Okay, all right. So now let's actually plug in the integration back. Well, first it's going to be kind of cancel out these negatives here. Okay, and then we're going to integrate this from 0 to 1. Okay. So let's plug in the 1 first. And so when we plug in our integration bound of 1, okay, we're basically going to plug in everywhere we see t, we're going to plug in 1. Okay. So we have t squared, so that's 1 over n pi sine of n pi, okay, plus 2 over n pi squared cosine of n pi minus 2 over n pi cubed sine of n pi. Okay. So everything in that square brackets there, that's our integration, evaluated at t is equal to 1. Okay. Then we're going to do the same thing and evaluate this at t is equal to 0. Okay, so we have a minus sign. square bracket 0 over n pi multiplied by sine of 0, okay, plus 2 times 0 divided by n pi squared cosine of 0 minus 2 over n pi cubed sine of 0. Okay, and luckily for us, in this case, most of these terms are going to cancel out, and we're just going to be left with just one term. Okay, because everything, first of all, we can see everything on the second term there is going to be 0, right? So 0 times sine of 0, that's omega 0, so that's definitely going to be 0. Okay. Next, we have 2 times 0 times cosine 0. 0 there is going to cancel that out. That one's also going to be 0. And then the third term in that expression there has a 2 times sine of 0. Sine of 0 is just 0. So this one also cancels out. Okay. Okay, so that one's pretty straightforward. Second one, on the upper term here, we have 1 over n pi sine of n pi, right? Since we know that n has to be an integer, so n has to be 1, 2, 3, 4. We've already seen this term before, so sine of n pi in that case is going to be 0. Okay. Same thing is going to apply to this last term here as well. Okay. All right, and so all we're left with here is just 2 over n pi squared cosine n pi. Okay. Right. And then one thing we can't forget, and so, this is very easy to forget, but don't forget this 2 that's out in front of the integration over there. Okay, so our an here is actually 2 times this. Okay, so our an is equal to 4 over n pi squared cosine of n pi. Okay. Any questions on this? We got this. Yeah.
How did you cancel the 2 over n pi cubed?
2 over n pi cubed. This one here.
Yeah.
So sine of n pi, we know n is always an integer, right? So that means that sine of n pi is going to be sine of pi, sine of 2 pi, sine of 3 pi. Yeah, so that term is always going to be 0. Yeah, that one's tricky. That one you have to kind of. All right, any other questions on this example here? Okay. All right, and so of course, we can write this out. And so if we evaluate this, let's just do the first 3 terms. Okay. So let's evaluate A1. So for A1, we're going to plug in n is equal to 1. Right, so we plug in n is equal to 1. We have 4 over pi squared multiplied by cosine pi. So cosine pi is -1. So A1 is going to be a -4 over pi squared. Okay. Let's look at A2. So for A2, we're going to plug in n is equal to 2. And so we have 4 over 2 squared times pi squared. 2 squared is 4. So we have 1 over pi squared. Cosine of 2 pi is just 1. And so that's just going to be a positive 1 over pi squared. Okay. And if we do A3, let's plug in 3 into this expression here. So that's 4 over 9 pi squared. Cosine of 3 pi is -1. And so that gives us a minus sign out in front here. Okay. All right. And so if we represent our function, so our half range expansion, say our even half range expansion. Okay. So f of t, right? So for any Fourier series expansion, we know f of t is equal to a0 plus summation n is equal to 1 to infinity, an cosine of n pi t over L plus Vn sine of n pi t over L. Okay. That's just our generic expression for a Fourier series expansion. We know that since we did an even half range expansion, Bn is equal to 0. So Bn is going to go away. We don't have anything there. And we're just going to plug in everything else into this expression. Okay. Because we have A1, A2, A3. We know that L is equal to 1 for this problem. Okay. So if we plug in everything for this expression here, we have f of t is equal to A0 we computed. That was kind of the first thing we computed in this problem. So A0 is 1 over 3. Then we have A1. So A1 is a minus 4 over pi squared. So minus 4 over pi squared cosine of pi t. Okay. Then we have plus A2. So plus 1 over pi squared cosine of 2 pi t. And then we have A3. So we have minus 4 over 9 pi squared cosine of 3 pi t. And of course, this continues on, so you could compute more coefficients if you want. But usually the first, for any problem you're doing by hand, the first 3 terms is usually pretty sufficient, pretty good. Okay. All right, and so that's half range expansions. And so, that should give you everything you need to finish that last problem on the homework. Okay. All right, and so from here, we are going to move on to the next topic, final topic for this second midterm, which is Fourier transforms. Okay. So, we're spending quite a bit of time on Fourier. Fourier transforms and Fourier series expansions, these are kind of two sides of the same coin. Because it represents kind of a pretty important thing. Okay. Okay. So the idea with Fourier transforms is to take the lessons that we learned in a Fourier series expansion and then kind of expand on that, kind of create another tool that is, similar, has the same spirit as the Fourier series expansion, but it's useful in some other different contexts. Okay. And it all kind of goes back to kind of our original kind of discussion when we first introduced Fourier about frequency and amplitude, right? So remember we talked about, we talked a lot about this idea of sound waves or sound, right? And so sound can often be characterized by the amplitude or the volume of the sound and the frequency or the pitch of the sound, okay? So Fourier transforms kind of builds on that idea and builds on our Fourier series expansion to kind of make kind of a technically a separate tool, a separate kind of calculation, but it is related to, our Fourier series expansion. Okay. So that's where we're going to start. So, just note that, every function has, some kind of frequency, some kind of amplitude. Okay. And in fact, a Fourier transform, we're actually going to extend our analysis to non-periodic functions. So that's kind of one of the main benefits of using the Fourier transform over the Fourier series expansion is that we can actually do this for non-periodic functions. Okay. So the idea is the following. So, you know, if you look at a typical Fourier series expansion, and the fact that we just did kind of an example like this is pretty good. Okay. If you look at the frequencies that are represented in this Fourier series expansion, not every single frequency is represented in our expansion. Okay. And so let me actually write that down first. So not every frequency is represented, right? If you look at how the Fourier series expansion is kind of constructed, right? And we look at the sines and cosine terms that we have, right? We're kind of limited by the fact that we're doing a discrete summation, right? So we're limited by the fact that our values of n, they're limited to just integers, right? And so if we look at just the previous example that we did, right? If we look at the frequencies that are represented in our cosine terms, right? They're all multiples of pi, right? So we have pi, 2 pi, 3 pi, 4 pi, 5 pi, and so on. Which, up until this point, when we're just doing a Fourier series expansion, that didn't really bother us all too much. All we were really concerned about was just representing our periodic function with the summation of sines and cosines. So it didn't really matter to us that our frequencies were discrete. Okay. But, if we wanted to see, what about some of the frequencies in between these discrete steps? What are the amplitudes of those signals? What do those coefficients look like? That information is kind of lost in our Fourier series expansion. Okay. Okay, so since we're doing a discrete summation, with with the exception of the frequencies that we actually land on in our discrete steps, all those frequency information is lost. Okay. But what if we're interested in that? And so, what if we're interested in those frequencies, that are in between those steps, especially if we have non-periodic functions. And so in either of those cases, if we wanted to get information on frequencies in between the steps, or if we have a non-periodic function where we can't even define what those discrete, frequency steps should be, then we need to modify our expressions for the coefficients in order to kind of, accommodate these situations. Okay, so that's kind of the first thing that the Fourier transform hopes to aims to remedy is, to kind of make this idea or to make this concept of Fourier kind of more applicable to a wider range of functions. Okay. And what you'll see is that, the expressions are not that, far-fetched. And so, they very closely resemble our expressions for an and bn or Fourier series expansion, except they are kind of more general. Okay. Okay, so I'll skip the derivation. So the derivation is kind of more or less straightforward, but we basically take our discrete summation and we take the limit in the case when, our frequency steps kind of get really, really small. Okay. All right, hello, can you guys hear me? Okay, I think the mic cut off for a second. Okay, anyway, so if we take the limit of our Fourier series expansion as the frequency step goes to 0, we're going to end up with the following expression. Okay. So I know that that expression by itself, there's a lot to that expression. It doesn't really kind of go over the full derivation, but so the full derivation is in the notes. But kind of the most important thing are these expressions here. Okay. Okay. So first thing we're going to get is we're going to get a function a of omega. Okay. So this a of omega kind of plays the same role as an in our Fourier series expansion. Okay. So this right here is derived from an. Okay. So our a of omega here is equal to 1 over pi integral from minus infinity to infinity. Okay. So that's one thing that we are, one of the big things that change. And so as the frequency step goes to 0, that's basically taking the same thing as taking the limit as L approaches infinity. Okay, so that's where that infinity comes from. Okay. And then we have f of t cosine of omega t dt. Okay. So you can see, it looks quite similar to our formula for an, except, first of all, there's no more n's, right? We have much greater emphasis on omega, and we're taking the integral from minus infinity to infinity. Okay. Okay. And then our b of omega, which, this right here is derived from our bn expression. This is equal to 1 over pi integral from minus infinity to infinity f of t sine of omega times t dt. Okay. So there's one more formula that we need to go over, but let's pause and kind of look at these two expressions here, and let's kind of talk about what's going on with these formulas here. Okay. Okay. So first, let's look at the left-hand side of these expressions. We have a of omega and b of omega. Okay. So that tells us that, when we evaluate these integrals, we're going to get a different function, but instead of being a function of time, we're instead going to be a function of frequency. Okay. So both a of omega and b of omega are functions of frequency. Okay. So omega here is a frequency. And the most important thing is that now our frequency is a continuous variable. So it's no longer constrained by our discrete values of n. Okay, now it's kind of a continuous kind of spectrum, you know, from minus infinity to infinity. So that's the first thing to note. So first thing is that, you know, now our frequency is an actual variable, and it's now a continuous variable that does not have any discrete jumps like it did in the Fourier series expansion. Okay. Now this also means that our time variable is not going to be present anymore, right? And that's because we're going to integrate it out. So the other thing we should note is that the time variable t is integrated out in these expressions. Okay. So after you perform these integrals, t should no longer be present, and so you should only have functions of omega. Okay, good. So that kind of brings up an interesting kind of perspective here, because, you know, by performing these integrations here, by doing these transforms, right, we've effectively taken our original function and transformed our variable into another one. Okay, so we went from a time domain function to a frequency domain function. Now, this is not the first time that we've seen this in this class, and so if you recall back, you know, back right before kind of midterm 1, we went over this idea of the Laplace transform, right? So in Laplace transforms, we took our original time domain function and we transformed it into the Laplace domain, or S. Okay, so that changed the variable of our function from t to s, and that changed how our function looked, of course, as well. Okay, this is kind of more or less the same thing. So in this case, you know, we are once again transforming our function from the time domain, and we're transforming it into a different type of function. But instead of the Laplace domain, we're transforming it into this Fourier domain type function. Okay. Hence why we call these expressions the Fourier transform, because they're transforming, you know, from one domain to the next. Okay. What's different about these transforms compared to our Laplace transforms, that these transforms actually do have a physical meaning. And so the frequency domain actually does have a lot of kind of physical intuition. It has a lot of kind of applications, right? The Laplace transform, we kind of just use that as a tool to help us solve differential equations. The Laplace domain didn't really mean anything physically. It was just kind of a tool that we were using. But the frequency domain in our Fourier transforms actually does have some physical meanings. And we're going to talk about some of those applications on Thursday. Okay. Okay. So these two expressions here combined can, you know, you can think of them as kind of the Fourier, one form of the Fourier transform of our function from the time domain to the frequency. Okay. All right. Any questions on this? Okay. All right, so that's good. So we have A of omega, B of omega. That's our Fourier transforms. These are what's called the sine and cosine transforms. So we'll go over another form of it on Thursday. Okay. Once you have your transforms, you can actually transform this back into the original function. Okay, by kind of putting it together in what's called the Fourier integral. So once you have expressions for A of omega and B of omega, So just like we did with the Fourier series expansion, we can take our coefficients an and bn and use those to represent our original function. So you can do kind of the same thing here. This is not that useful all the time. Usually when you're doing the Fourier transform, you're just interested in just the transform. But this is just to kind of remind you that this is all connected back to our Fourier series expansion. Okay, so we can use this. We can use them to represent our original function, and this has a name. Okay. So whenever you represent your original function in terms of its frequency domain components, we call this the Fourier integral. Or in other words, the Fourier integral representation. Okay, so we have f of t is equal to, so f of t here, this is our original function. Is equal to integral from 0 to infinity of a of omega cosine omega t plus b of omega sine omega t d omega. Okay, so it's basically just taking, taking our Fourier transform, coefficients or expressions, whatever you want to call it, a of omega, and then using that to represent our original function here. Okay. So if you look at this expression carefully, this is basically meant to represent or kind of, be very reminiscent of our Fourier series expansion. Except instead of a discrete summation, we instead replace that with an integral. Because now omega is a continuous variable. Okay. Any questions on this before we do an example? Okay. All right. So very quick example before we head out for today. Okay. So this problem here is very similar to what you're going to be doing on homework 6. Okay. So in this example, let's find the Fourier integral representation. Okay. And so we're gonna find the Fourier integral representation of the following function. Okay. So we have f of t is equal to, we have a discontinuous function here, and so that's that's kind of a theme. So f of t here is going to be 1 when minus 1 is less than t is less than 1. Okay. And then everywhere outside of that interval is going to be 0. Okay. So if we plot this out, just for visualization purposes, it looks like the following. We have kind of a little bit of a square pulse here. Okay. Now this is a little bit different compared to our previous problems, because this right here is a non-periodic function. Okay. So, kind of the implication for all the previous examples that we did was that we assumed that that pattern that we described with the function here is going to repeat. Okay. But if you look at see how this function is defined, we can see that this function is 0 everywhere outside of this interval. Okay. So that means this function here is, it's a discontinuous function, but it's not periodic because this square pulse is not going to repeat itself. And so we wouldn't be able to find a Fourier series representation of this because, it's a non-periodic function. And so if we wanted to represent this with Fourier in the frequency domain, we'd have to use the Fourier transform. Okay, can you guys hear me? Okay, good. Microphone keeps cutting out. Okay. Ugh. Okay, well, hopefully the microphone stays active. Okay, so let's compute A omega, B omega, okay? By the way, if you look at this function here, you know, this is very reminiscent of an even function, right? So if you look and see, it is symmetric across the vertical axis. So that is going to play a role in how we compute things, okay? Okay, let's first compute A of omega. Okay, so our expression for A of omega is 1 over pi integral from minus infinity to infinity, f of t cosine omega t dt. Okay. Okay, so let's go ahead and plug in for this function here. And so even though our integral here is from minus infinity to infinity, we know that our integral is going to be 0 everywhere outside the interval from -1 to 1. Okay. So since f of t equals 0 outside of -1 less than t less than 1, okay, we can then modify our integration bound to go from -1 to 1. Okay. And so this is going to be is equal to 1 over pi integral from -1 to 1. Okay. Our function in that interval is equal to just 1. And so we're just going to integrate cosine of omega t dt. Okay. Okay, so let's go ahead and evaluate this integral. This is pretty straightforward. We don't need integration by parts here. So this is going to be 1 over pi omega multiplied by sine of omega t evaluated from -1 to 1. Okay, so if we plug in these integration bounds, we have 1 over pi omega multiplied by sine of omega minus sine of minus omega. All right, so let's take advantage of the fact that sine is an odd function, and so sine of minus omega is equal to minus sine of omega. Okay. Okay. And so we have sine of omega minus sine of omega, so the two minuses are going to cancel out. And so what we get for A of omega in this case is 2 sine omega divided by pi omega. All right. Any questions on how we got that result there? Okay, so very quickly, let's compute B of omega. And so we have B of omega is equal to 1 over pi integral from minus infinity to infinity f of t sine omega t dt. Okay. Right. We're going to do the same trick here. So since our function is 0 outside the interval from -1 to 1, so let's go ahead and apply that to our integration bound. So this is 1 over pi integral from -1 to 1 sine omega t dt. Okay. So we perform this integration. We have 1 over pi omega times minus cosine omega t evaluated from -1 to 1. Okay. And just because we're almost out of time, I'm just going to go ahead and kind of write the solution for this. And so this 1 over pi omega minus cosine of omega minus plus cosine of minus omega. Okay. Let's take advantage of the fact that cosine is an even function, so it's cosine of minus omega is equal to cosine of omega, right? We're kind of just eliminating that negative because cosine is even, okay? So you have minus cosine omega plus cosine omega. Everything in that parentheses is going to cancel out. And so what we get as a result is b of omega is equal to 0, okay? Which is consistent with, what we expected because our original function had that even pattern. So it was kind of symmetric across that kind of vertical axis. Okay, so it makes sense that b of omega is equal. Okay, so when we come back on Thursday, we will kind of continue on with this discussion of Fourier transforms. We'll talk about the complex form of the Fourier transform and what that looks like, and then do a couple more examples. All right, so thank you guys for coming today. Remember, the midterm exam is postponed, so it's not going to be next Thursday. It's going to be the following Tuesday after that, April 22nd. We'll kind of plan accordingly. I'll post a study guide next week, and I'll see you guys on Thursday.
So I literally just like fun.
I was touching on homework.
Yeah.
I pretty much got all of my answers like wrong, but like not to a bad extent. That's the coefficient issues. Why is it all negative for the second solution? That's one thing I was having trouble with.
I have to look at my solution, but what did you get for these ones?
For one, wait, let me see. Okay, yeah, because my coefficient was -8 cosine pi to the n.
Yeah,
So if I plug in 1, I get cosine of pi, which is -1, which turns this positive.
right.
So I get 8 over pi, so that's positive. So I don't understand how it's, I guess the word is why it's oscillating.
Yeah.
If cosine's changing every time.
Yeah. It does look right. I mean, the 8 over pi n is right. That's kind of the pattern that you see there.
Yeah,
I mean, it should be changing sign unless that cosine n pi is not. I'll have to check my solutions, just double check.
yeah, because the other thing would be like, obviously, yeah, like you just said, the cosine of pi would have to not be there.
Yeah. Go ahead. I'll double check with my solution.
Okay.
And then I'll get back to
Do
you.
you mind if I email you all three?
Of course,
Because
yeah,
I had
yeah.
issues with all the
Yeah,
coefficients.
of course. Yeah, I'll go over tomorrow.
Thank you, Professor.
Yeah. Mhm.